Okay, right. So the next thing I'm going to teach, I'm not going to do D. It's very repetitive. Okay, so it's very straightforward. So the next thing I'm going to do, I'm going to combine two subtopic together. Okay. So the next thing that we would like to address is we are going to talk about eccentric unsymmetrical loading. Okay. So if we look at eccentric unsymmetrical loading in terms of formula, basically we have stress X, and then this is equal to Px over A plus, in fact, the Px over A is also plus or minus. Okay, it all depends. Okay, and then plus or minus my over Iyy multiplied by z plus or minus mz over izz multiplied by y. So a loading of this sort, how does it actually look like physically? Okay, but before I go on, so what is the difference is this px over a is the axial load, right? And the axial load is not equal to 0. When it's not equal to 0, that's where we have the term eccentric. Okay. And over here, you have moment about y and moment about z-axis, right? So when you have two moments, right, that's where we have the unsymmetrical loading. Okay. So how does a loading of eccentric unsymmetrical look like? So I'm going to sketch over here, right? So the sketch, the axis, you have to define your axis first. So this will be my this will be my oh no, not this way. Oops. So this will be my let me see what's the best way of sketching this. I'm not getting the orientation right. I think this is the best. Okay, so this is my x, and then this is my y. Okay. And then we have another axis over here. This is my z. So from what we can see from these equations, okay, basically based on loading, we have, this is just an example. We have moment about z, sorry, moment about y, right? You have moment about z, and then you have axial load px in this direction. Okay. So now if I'm going to sketch a structure now, I'm going to sketch a So this structure looks like this. Okay. And then this structure will go into a wall. Like this. Wait. And then at this end, it's built in. Okay, or I'll draw. Yeah, it's built in. So there's a wall down here. Right. So we know I'm going to sketch the geometric centroid. Right. So the geometric centroid looks like this. Okay. And then another geometric. This is position of the other geometric centroid. And then we have another position. Okay. And then there's a moment applied. Okay. Or there's an axial load applied. And the axial load is coming out in this direction. Okay. So this is our px. Okay. And then we have two distance now. Right. The distance from here to here, I'm going to call it A. And the distance to here is B. Okay, so this distance is A, and that distance is B. And then if we were to look at moment about Z, right, based on Px, right? So moment about Z, right, we know right, moment about Z is equal to force, which is Px, multiplied by the perpendicular distance of B. And the orientation you're doing is this way, right? So this is under compression. Anything on top is under tensile, right? This moment about Z. And then moment about Y, right? It will go about in this orientation. Okay. And moment about Y is equal to Px multiplied by A, right? So over here, you can see that this is compression. Oh, hold on. Yeah, this is correct because of how it's drawn, right? And then this is tensile. Okay. So this is how eccentric unsymmetrical loading looks like. Okay. So now, if now we were to do, okay, so this is for what I'm drawing down here. Okay, what you see that I'm drawn down here. This is for a single material. When I say a single material, the whole thing, for example, the whole thing is made of, for example, steel. Okay, steel, for example. Okay, So now you understand what eccentric unsymmetrical loading looks like. Basically, Px over A is not equal to what? It's not equal to 0. Okay, it's not equal to 0. And I do beg your pardon. So if I were to properly draw the transformation, this is our moment in the z-axis. Okay, it's not following the green line, whereas my, I have to draw properly. I don't want to confuse you guys. This is how my look like. Okay, and then the red, this is our mz. Okay, right. So this is for a single type of material. Okay, so formula really straightforward. Okay, so now when is it positive, negative? So when it's pulling out, right, like it is now, it's in tensile. If the arrow reverse, right, px is then going to induce a what? Compression. Are we clear? Okay, if it's pulling out, it's in tension. Now I'm going to incorporate this topic over here, right, by looking at a composite. Okay, by also incorporating composite or sandwich material. So for your term test on 6th of June, okay, you'll be test until composite. So this is included as the last topic for term test 1. Okay, so this will be included. Okay, so let's focus on composite material. Okay, and the first thing I want to do, so we know, right, composite material that is under axial loading first. Okay, so we want to look at the I'm going to go two materials for two type loading for composite material. One is under axial loading and the other one is for bending moment. So let's focus on composite material. Under axial loading. Okay, so we have, this is our x, this is our y, and we have our rotation about z. Okay, so a sandwich material, how does it look like? So basically it looks like this. Okay, right, so this is material number 1. Over here is material number 2. And we want to go through axial loading over here. So this is our px, right? This is our px. Okay, so we are aware if there's a px over there, right, so the material for material 1, it will be under the load P1, and for material 2, it will be under a load P2. Okay, and then overall we have our original length. This is our L0. So if we look at our cross-section view, I'm going to sketch our cross-section view. So this is our Y, this is our Z, This is our rotation about X. So the cross-section view looks like this. Okay, so this is our cross-section view. So this is material number 1. And this is material number 2. Okay. And material number 1 has a Young's modulus of E1. Material number 2 has a Young's modulus of E2. So E1 and E2 are Young's modulus. Okay, they have their Young's modulus. So when the structure is under load, right? So you have P1 and P2 over there. The structure will elongate or deform. And it will deform to a new length. And this new length is what we call L1. Okay, that is our L1. So we are going to, over here, this line over here, okay, this line over here that I'm shading now, we are making an assumption. Okay, so over here, by drawing that, we are making an assumption. We're going to assume. And the assumption is the strain induced on both materials are the same. Okay, we just make the assumption, okay, just to simplify our calculation. That's all. Okay, and also this is only true. You can make this assumption also, and the other thing is we're also going to assume, or you can only make this assumption. This assumption can be made okay, if